In this section I'm going to be showing off the n-body simulator I created. It's been compiled and it's just here. Here's where it shows how many bodies in the collection, and this is where I can create new collections of particles, load them, save them, delete them. I'll just load up a system or collection I created earlier. It contains the Sun, Venus, Earth, Mercury and Mars. This bit I can add particles to the system. It has to be dimensionally consistent. The program can work in any number of dimensions because once I've defined vector addition and basically vector arithmetic, the equations of motion in the Cartesian plane are basically the same. So I can add them using by inputting the Cartesian coordinates here, or orbital elements, and this section down here, the orbital elements, just takes the orbital elements and converts them to the initial conditions in Cartesian coordinates, because we're obviously, as I said in the documentation, this program is using a Cartesian coordinate plane, coordinate system. Okay, these are the plot settings. So I'm gonna name. This is the name of the plot. Okay, because I can't have an animation in 3ds Max going on for a year or whatever, I've got to scale down the time. Also, I can't have a scene the size of a solar system in 3ds Max, so I've also got to scale the size down, the physical dimensions, which is this bit here, world scale. Okay, so if I input, this is a Excel spreadsheet I collected of all the orbital elements, initial Cartesian coordinates, mass, radius of all bodies in this solar system, including some others here. And this timescale here is I calculate it so that it when 1 second passes in the system, a month passes, and also this world scale just ensures that I can fit the solar system into this max, this 3ds Max scene. Anyway, the calculate increment is basically how long in seconds between when the acceleration is calculated. So if it was 1, every second it would calculate the acceleration and then plot increment, the position and the velocity, like I described in the documentation. Anyway, I'm going to put this to 6, and I'm going to change the output increment to something large. Here we go. And the output increment is just how many seconds between export of the positions, because this program is just exporting the max file, and obviously I don't want it to export a line to the max file, a line defining where the position of the body should be every 6 seconds, because the max file will just get huge. So this value here of output increment is basically when how many seconds does the program output a line. So it's quite a large number, but it's still small enough to create a smooth animation. So there's a frame every this many seconds, and the duration is just the time in seconds that the simulation will go on for. So that's 1 Earth year. So to conclude, we're plotting for 1 Earth year. We're calculating the acceleration and the displacement and velocity every 6 seconds, and we're outputting a line to the max script every 81,000 seconds. 82,000 seconds, and we've scaled it down. We've scaled the time down so that when 1 second passes for us, a Earth month passes. And okay, I'll just plot it. My max file is located here. If I just import this here, and you can see this is the max file that's been generated. 30 frames in a second, and so this animation will go on for 12 seconds, which is about right because there's 12 months in a year. So if I evaluate this, it now imports, it uses all the data from there, and we now have our system in Max, so it's ready to visualize. First thing you notice is that the planets are so tiny. This is the sun here. This here, that's Earth. Believe that's Venus. Earth, Venus, no idea where Mercury is. That's Mercury, and that is Mars. And this is perfectly to scale because we've kept it consistent. So as you can see, this is looking at all the system, and it's clearly way too small. So I'll show you a system later, in perhaps in a different video, where I've scaled up these the radius of the planets just so they're visible. But from now, you can see that they're just by the crosses. These are the planets. Anyway, if we look top down, it gives us a better representation, and I just change this. So 1 second is a month, and we can see that Earth is this one here, that little guy there. So just analysing Earth, we can see that it's going round. And it returns perfectly to itself back again. And although the animation is looping, because this is a perfect year and it's returning to its initial position within the initial velocity, as it should, because it's Earth, the animation can be looped. Whereas if I look at the other planets, when it gets to here, they jump because they're not returning to the same place before it starts the animation again. This can be solved by looping the frames in which it does return to itself, but I will do that in another video. Anyway, so you can see this is pretty damn accurate. It's returning exactly to the same place in the correct amount of time. And Mercury's going very fast. Obviously, the precession of Mercury isn't in here because it's Newtonian gravity. But all of these planets are experiencing small perturbations because of the n-body simulation. In fact, an interesting thing to show is if I zoom in on the sun, sun here. Obviously, in the one body simulations like Kepler's problem, the sun wouldn't move at all because it would be the immovable object or the fixed object, and the test particles spinning around it will be moving. Although in the n-body solution, just to prove that this is an n-body solution and not a collection of Kepler problems, you can see that the sun is very, through the course of a year, it's noticeably moving, only a couple of meters or so, but it is being the gravitational attraction on it is causing it to move a slight amount, and that's being accounted for in the n-body solutions simulation. Okay, that concludes this section. I'll go into further detail in a later video.